Hey there data people, and welcome back to the lab. Today we'll learn about multi-project CI/CD using the free tier of GitLab. We'll deploy an ML model with Docker on top of our data lab infra, and we'll close with a full retrospective covering the good, the bad, and proposing an architecture redesign that covers the pitfalls of our original approach. Remember, small steps and continuous improvements is all that matters, so leave your ego at the door and come on into the lab! So our goal today is to deploy our application. And in this case we are going to deploy an ML server, an ML endpoint for our model. So this video will be the next video or the last video on our data lab infra series, but also the next video on our MLOps series. Our goal is to deploy this using Docker and our CI/CD pipeline. So one of the first things I did was to try and improve a little bit on do a little refactoring here to improve how this is organized. So I replaced all the inline scripts with a single call to a script, and I dropped these scripts under the CI scripts directory. But unfortunately this ended up not being the best approach, because we will need to use multi-project pipelines, and this will be called potentially from other projects within GitLab. And when you do that, particularly using the needs project API, you won't be able to run scripts because these scripts won't exist on your external repo. So I ended up going back on this refactoring, although it would have been much cleaner to do it this way, but I ended up going back on this. So let's go back into our current version, and as you can see, I ended up dropping that, moving it back to the root again, and now we have also these provision scripts, which I'll get into in just a minute. Another thing that we did here was create a custom Ubuntu image, and this was useful because we needed some dependencies frequently, like curl or JQ. These were two of the most common ones, and doing this and pushing it to our container registry enabled us to just use that image instead of having to run all these commands on the before script tag for each job. So let's see if we have one example here, and as you can see there is one here. So before we did this, we would have a before script here with a bunch of other commands that would apt update and upgrade and install JQ. And the fact that we don't need to have this ran every time anymore, this improves the performance of our jobs each time we run them. We also had to reconfigure something within our GitLab deployment. In particularly, we had to add this option to disable checksum for min.io. Otherwise, when we pushed this Ubuntu image, because it was large enough, it would trigger the checksum validation, and this would fail because it just doesn't work correctly with the min.io here. Actually this is somewhere within GitLab's manual, so we ended up disabling this, and it works perfectly fine. Another thing that we did was to improve the CI/CD workflow for Postgres. So credentials are no longer printed in logs. This was an awful decision. They are instead stored as JSON within a CI/CD variable. And external projects will always need to call this workflow to load the credentials into the env. If the database and credentials need to be required, they will be required and then returned. And so let's take a look at Postgres, where it's doing exactly. So it first tries to load the credentials. We are using our custom image, and so it checks this pSQL secrets variable, which should be in CI/CD. If it's not, it will default to an empty JSON object. Then we'll try to extract the DB user from these credentials. So the format is user password, as simple as that. And we'll then export this as environment variables. If there is no password defined, this means that the user doesn't exist yet. And so we use this .env and pass it to the next job to create the user. And in here we'll have a script where we test whether this DB pass is empty. If it's empty, then we'll generate the password. We'll run the SQL commands to create this user, and then we'll update the pSQL secrets variable with the new user. So we can concatenate with the existing object, the new user and the new password. And then we use the REST API for GitLab with our GitLab token to update this variable. We first check whether the variable exists. If it exists, then we update it. If it doesn't exist, then we create this variable. And that's pretty much it. We export this yet again to the next job. And for the create DB, we'll have access to the DB name, to the DB user, and to DB pass. These last two will come from the previous job. We'll then create the database and grant privileges to this DB user, and we'll export this so it can be used by any following jobs. And the following jobs are usually from this provision over here. They are called from provision. So provision are templates that are not included on our local GitLab CI, except if we want to provision something particularly, but as you can see, they are not included here on the main block. And for instance, for Postgres, and they are all essentially the same, we'll have a provision something over here, and what it does is use the GitLab API to trigger the pipeline on the other project. So we require a GitLab trigger token on the created from the original project, and you can create this within the CI/CD settings. Let me just quickly show it to you. So if you go into our Data Lab project, let me just open third tab. You can go into CI/CD over here, okay, and under pipeline trigger tokens, you can simply add a new token, give it a description, copy this token, and set it up as the variable GitLab trigger token within the repo where you want to use this provision DB. And so we just trigger the pipeline and get the ID for that pipeline, which we will then return in here. And we'll also wait, we'll be polling for the status every 10 seconds. And if we get a success or fail status, then we exit this provision job. We use this exact strategy for Llama and Kafka as well. And that's it for those. But for Postgres, because we need a way to return the credentials as well, we also have a job to get the job ID for the credentials creating job, which is the last job on our Postgres pipeline. And we just query for this and return the ID. And so this get DB credentials job ID will return the pipeline ID as well as the job ID. And then we have a job to fetch the credentials, which is the actual job that we call from our external projects. And this will essentially just download all artifacts and use them to load some environment variables. The artifacts over here, if we go into Postgres, as we can see, this is an actual file that we expose, and this expires in 15 minutes. So this is just to be used by the pipeline that is calling this one, and then it will disappear, just because we cannot use reports on the free tier of GitLab, because we have to use the REST API. So this is a workaround if we want to do it this way. And keep in mind, this code is available on GitHub. You can check it out in more detail by yourself later, but this is the overview. We also set up an external project to test our CI/CD provisioning jobs, and you can find it on GitHub as well. It only contains a GitLab CI file, which looks something like this. So we've got a bunch of global variables. We are going to create these CI/CD prefixed resources just for testing, and we've got our provision and test stage, and we can include the files from our original project. So datalab tech.tv/datalab, this should be your GitLab project. We are including the infra branch, and then we can set the particular file that we need. For instance, we need a provision Postgres in here, and we pass it the inputs. So these included jobs will run, and then you can just set up your own jobs. In this case, we just test whether the DB connection is working, or whether the Kafka consumer was properly created, or if the model for Ollama is available after the pull or after the topic creation. And for instance, in here we need the fetch DB credentials, which comes from this provision Postgres, and we check whether we can connect using the DB pass, DB user and DB name as provided by that external job. We do something similar for Kafka and for Ollama as well. We were also required to increase the concurrency for the GitLab runner, because by default it's set to only 1. So we had to go into our platform and GitLab TF, and of course we did this manually. We did not redeploy it, we just added this over here, and we need to add this set to replace concurrency equals 1 by concurrency equals 4, and this is enough so that one job can trigger another job and wait for it. For this test project, we are running the GitLab CI pipeline on every push, and so the output will look something like this. You have 2 stages. The first one is the provision stage, which is the stage that we assign to the included CI provision files from the original datalab project. And then we have the test stage, where we run jobs locally to test whether the DB was properly provisioned, whether the topic and consumer were properly initialized, or if the model is available. This will look something like this. For instance, for Postgres, we'll run provision DB, get DB credentials job ID, fetch DB credentials, and then we'll test the connection. If we go into this job, we'll see something like this. As you can see, because this command didn't fail, the job was successful. It means it connected, so this is working. And we do something similar, for instance, for Ollama. As you can see, we are waiting for the job. We are polling essentially, instead of using the premium API, because you could do this with needs project for GitLab, but unfortunately, as you can see, this is only premium and ultimate tier, and this would let you set artifacts to true over here, and you wouldn't need to worry about all that complexity with using the API and curly requests and all that. So if you have something on a more professional level, you could pay for premium and use that instead. It would make sense. But instead we are using this trigger pipeline with a trigger token, and we are just posting to this endpoint and using what is available within the free version. So for model deployment, if you remember our ML end-to-end video, and if you don't, you can go check it out, it's under the MLOps playlist. We had trained several models and logged them using MLflow. So we'll have our serialized models available over here, the ones that we want to call from our REST API. Our strategy here is to just create so we have our ML server, which is a FastAPI that provides the required endpoint. So we've got this inference endpoint where we can run a regular prediction, or we can even run ABN testing, and we want to expose this on our data lab infra, and we'll use Docker for this. And so what we do here is under infra apps, and keep in mind this is a local project, but we could of course do this on an external project. In here we just create a Docker file. We use UV as our base image with Python 3.13 and Debian Trixie Slim. We install Git and curl. We need Git because we are going to download a Git dependency from within our pipe project. We switch to /datalab, which will be the directory where our datalab repo will be copied to. And first we only copy the pipe project and the UV log files, so we can install every dependency. We do this because if we change any files on our ML package, our own Python files, we do not want to have to rebuild the image completely. So this will be cached if we don't change any dependencies. So we then copy everything and we run uvsync again, just so that it installs our own package, and it should be at this stage it should be instant. And then we use this custom entry point. Also keep in mind that we are running this from the root directory, because we need our .env for some custom variables like MLflow tracking and Kafka broker endpoint. We'll get to that. And so we run this custom Docker entry point, and this is why the path is from root. And in here we just set errors, so that if we can't activate the virtual environment, this will crash immediately, this will exit. And we run the lctl ml server with any arguments that you might want to pass to Docker when you run it, but the default should be fine. And then we build this Docker file from Docker Compose. Like I said, we use the root directory as the context, so that .env is loaded automatically. We expose this on port 8000, and we only configure 2 variables, although we have more environment variables that need configuring. We only configure 2 of them. Some other variables are configured in the CI/CD pipeline, and some variables are not configured here at all, because they are for the Duck Lake, and we haven't migrated from SQLite to Postgres yet on our Duck Lake, so we are just not using the logging feature. So each time we do an inference request, we have the option to log that inference request to our Duck Lake, but we are not enabling that option for now, because we will cover SQLite catalog migration for Duck Lake from SQLite to Postgres in the next video. So In that video we'll re-enable this and show it working completely. And so we just set the ML flow tracking URI and Kafka broker endpoint. This is set on our .env. This should be set to the Docker shared host, which is running on our Data Lab Infra. Same thing for Kafka broker endpoint. And this will be called from our CI/CD job under deploy. So we have these applications, and as you can see, we are provisioning 2 required topics using the CI provision, just because this is, although this is the Data Lab project, not an external project, we use the same workflow to call it from our own project. And then we provision these topics, topic group, and also here for inference results and for user feedback. And then we can, as you can see, set these as dependencies for our apps deployment. And we set these additional environment variables, which will be passed to our application. And then we run Docker compose up with build. Build would build the Docker image every time, but since we use Docker build kit, we set it to 1. Here there will be caching through the build kit, so you can run this with -- build every time. If you don't use -- build and do any change onto the Docker file, then it will not be rebuilt, so we really need this here. The best strategy is to just use caching like I did. And once you have this working, we can go into GitLab, and let me just show it how we will do this. So now we have a boolean flag to force redeploy, rerunning the deploy workflow. So let's do it for the apps deployment, and let's run a new pipeline for this. And as you can see, we are calling provision ML server feedback topic as well as results topic, and this will trigger 2 downstream jobs which are on the same project, but they might not be. If you go into the jobs, you'll see that there are 2 jobs or multiple jobs running over here. So we have our provision Kafka topic for both topics, and we have our init consumers. As you can see, these have been created and the variables have been passed to our Docker compose script. So this job will be responsible for redeploying our Docker compose project. And this is essentially what happens after a while building your Docker image. You'll get this deployment, and we run Docker PS at the end, just make sure that this was at least started. And as you can see, health starting over here. This is running on port 8000, so we can go into Docker apps port 8000, and we should find an API running here. So we'll have can go into docs and we'll find the FastAPI Swagger UI, and as you can see, we should be able to call one of our models, for instance XGBoost TF-IDF, which is one of the models registered within MLflow. If you go in here, XGBoost TF-IDF, and let's use the latest version and disable the log to Lakehouse, because this is not currently working. And if we execute this, we'll see that we get our prediction back. We can also check the logs for our Docker container. If we go into portainer and we can go into Docker apps over here. We'll find that our container is running, and we'll have access to the logs over here. And as you can see, there are no errors. The artifact, let's disable auto refresh. The artifact was correctly downloaded from MLflow, so this means the model is available, and the inference was run for this model. So now that we were able to create all of this data lab infrastructure on-premise using Proxmox, we've got our 4 layers, from the foundation layer with MinIO, platform layer which includes GitLab and Docker instances, the core services layer with Postgres, Olama, Kafka, all the services that we need, and finally today the apps layer. We did some reflection on every decision that we made. So let's go into our first retro for this data lab infra architecture. So what went well here? For our architecture, the architecture was deployable. So nothing really changed from our initial design, it just works. Like I said, everything works. And then for GitLab, we were able to create a custom Ubuntu image that sped up CI/CD jobs, and this made the container registry already useful, which is good. But we've got a lot to improve still. So our Docker VMs, using multiple Docker VMs was a bad move, just because we have so little resources. A single beefier instance would have been better. It's easier to resource pool. We also have a single GPU that we cannot virtualize, so it will only be available to a single VM. It would be great that our applications and our core services could both use the GPU, so Olama can use the GPU as well as our model can use CUDA for deep neural networks. And also there is lower service communication overhead because they are all within the Docker network that can communicate directly within that. For secrets management, we had this amazing idea of using GitLab CI/CD variables exclusively, but this turned out to be to introduce more complexity than we'd like. So using GitLab for secrets management alongside a .env and a Terraform's tf vars file, as well as tf outputs, because sometimes we need passwords or credentials to provision some resource, but sometimes we also produce passwords using the random password resource within Terraform, and we need to output those passwords somehow. We are currently using Terraform outputs, which is not great at all. So one better way would have been to just deploy HashiCorp Vault into our layer 1, the foundation layer, the same layer that has MinIO for S3 object storage. And for the local deployments, if you don't want to, have all your on-premise infrastructure, if you just want to run it locally, just add HashiCorp Vault to the dev profile in our compose file, and that would solve secrets management a lot better. The conclusion I came to is that it's not overkill at all to use HashiCorp Vault, despite it being an extra service that you need, and we are trying to look for a minimal setup that works. It just ends up being too complex to manage secrets the way we did it, so it's completely justifiable to use HashiCorp Vault here. And also we can use the Vault agent to load secrets as environment variables, so this we can really replace the .env and the Terraform tf vars with a single try, and also store our output passwords there. And finally, like I was saying, Terraform has a Vault provider that you can use for input and output both. For image management, our container registry is still underutilized, and this is mostly because we need a better workflow for building images. Right now we have this Docker folder within our Infra services or Infra apps directories, and it probably is better to extract this and create a top level Docker directory where we manage our images separately, because we might want to update the image without touching the infrastructure. You know, it just triggers a redeployment but doesn't do anything different, or maybe we just keep the same version for a while and we keep it separate. I think it's justifiable to have a separate workflow to manage images. So now let's get into some of the GitLab pitfalls, and my main pet peeve here is bloat. GitLab feels quite bloated, especially for a small home lab, and I'm talking about the Omnibus installer here, because you can customize a lot by doing your own installation, and even through the Omnibus installer by disabling a few services. So Postgres in our infrastructure is duplicated in the L3 services layer. So layer 3 builds on top of layer 2, which builds on top of layer 1, and Postgres is running on layer 3, but GitLab is running on layer 2, so we would need layer 2 to be able to deploy Postgres, but we might decide to move Postgres elsewhere to make this shareable for layer 2. Prometheus, which is used for metrics, but we don't really care for metrics on a home lab scenario and for our particular use case here, so we might disable this, and this is usually a memory hog. And also there are a few pitfalls regarding CI/CD. There are no separate workflows like GitHub Actions or Gitea CI/CD, and we had to do our control via input existence or absence, so we check whether a variable is set or empty, or trigger flags in the case of our deploy workflow. And also GitLab has, in my opinion, some pitfalls regarding monetization, because monetization is dependent on feature tiers, and I don't think this is the best approach to monetization. For example, when you are trying to use a multi-project pipeline with the needs project feature, it only works on paid tiers. So you end up trying to write these configurations that don't work, and you don't get clear feedback on why it's not working unless you check the documentation. So I didn't particularly like this. And also regarding tools and documentations, you've got GitLab Rails console that takes nearly 30 seconds to start. This is a common issue with interpreted languages. The more dependencies they have, the more time a tool will take to start. DataLab is the same, so it's just really an issue with interpreted languages. And documentation is hard to browse, due to project complexity and dimension. This is really just the reason. So this got me thinking about whether Gitea would have been a better option. Maybe it would have been a viable alternative for our needs. We need a container registry, which Gitea has, a CI/CD runner, and Gitea recently added the Act runner as well, and variables and secrets, which it also has. So maybe we'll explore this in a future video and try to test whether GitLab would have been a viable alternative here. We also use Init containers on our Docker Compose, so we use some containers that exit after initializing Kafka topics or pulling some default Olama models. but we could scrap them in favor of CI/CD jobs. We already have the jobs. We just need to, kill that workflow completely. We don't need to set those environment variables. We just do it via CI/CD. And regarding project organization, it got me thinking, would a single unified project for all layers of the infrastructure be better? A single Terraform project, a single Docker folder within Infra, everything would live under Infra. The architecture and its layers stand on their own, the design, the theoretical design is still layered, regardless of whether we use a single project to manage this. But it's unclear how it would affect complexity. And right now, each layer is easy to manage, although there are multiple commands that we need to run, because we need to run Terraform apply for one folder, Terraform apply for the other folder, for each layer, but we've got a just file that ties it all together. So, I'm not sure whether I would split this. Right now it's quite, the projects are quite focused and small, so I don't really see a reason to split it, just part of a thought process here. For configuration management, we are not using Ansible, and this was a bad move, because Cloud Init is great for provisioning standard VMs, but not to handle mutable configs. So each time I needed to change something on the config, I had to do it manually and then update the Cloud Init config, or destroy the instance completely and recreate it. So I would use Ansible if I was beginning again. Caching, a proxy cache or a general caching strategy within CI/CD would be useful here, because we are, designing our workflows and we do multiple requests to package repositories, be it apt, apk, or even, PyPy. So we do this during the initial coding stage, like I said, but also we do this continuously when we install packages within CI/CD runners, particularly when we had the before script where we were continuously installing JQ or something like that. And finally, we are using SQLite for everything, because this was deployed to run locally, but when we could really be using Postgres. So for MLflow and Duck Lake, we are currently running on a SQLite backend, but both support Postgres. So in a future video, we'll do some migration from SQLite to Postgres, particularly for the Duck Lake, which will be our next video. So now let's talk about architecture redesign. And we proposed a new architecture design where we keep our foundation layer, our platform layer, services and applications like we did before. But now we have a lot more services on our foundation layer. So for our foundation layer, we added Nginx, which should work as a proxy cache for apt, apk and everything else that we need. We added HashiCorp Vault for secrets management and configuration management. We explicitly showed here that we are using Terraform, which we were already on the previous approach, but we also now added Ansible, and we kept min.io. For layer 2, we simplified our Docker deployment. We'll now have a single Docker VM, and we also explicitly show here that we are using Terraform and Ansible. And we, pending testing of course, we are going to explore Gitea as a viable option. We didn't add any Postgres to our platform layer or our foundation layer yet, because we don't know how the deployment for Gitea will be done, but we might add a Postgres instance to our platform layer instead of it running in here on our services layer, so we might promote it to layer 2, right? In here we kept things the same, but we extracted Duck Lake to this L3 edge layer, because this is really running locally on DuckDB on your machine, and Duck Lake will connect to Postgres for the catalog, as well as layer 1 for MinIO, so for S3 for your object storage. And finally, layer 4 is exactly the same. We just added Node.js as an example of a web app, a generic web app that we might want to deploy, for instance, because we are creating some visualizations that are dynamic and we want to share via a website, a microsite, something like that. And so this should be a part of more videos on GitLab Infra in the future. And there you have it. This wraps up this series. I hope you enjoyed today's video or found it useful. If you missed any of the previous videos, you can find them on the GitLab Infra playlist. You can also find this video on the MLOps playlist, because we talked about model deployment here. In the next video, I'll explore Duck Lake catalog migration from SQLite to Postgres, and this will let us re-enable the lakehouse logging on our ML server that we deployed in this video, and finalize our data stack setup. As usual, this week's blog post is available at datalabtechtv.com. Follow the channel on Blue Sky for updates, and join Discord if you have any questions. Don't forget to drop a like and subscribe for all things data.